Okay, so here we are on question 3, which the first part of the question is explain what is meant by the temperature of a substance. So this is straight from your definition. Temperature is proportional to a measure of the average kinetic energy of the molecules of the substance. So it's a measure of the average kinetic energy of the molecules in a substance. Straight definition. Okay, you need to make sure if you wanted 2 marks, that definition had to be very clearly stated. You need to make sure that you get everything right there. Okay, now the second part of the question. A thermometer is placed in a liquid contained in an open beaker. The reading of the thermometer is recorded at regular intervals. The variation with time of temperature theta is shown below. So the temperature of the surrounding is 20 degrees. On the graph, continue the line to show the variation with time of the temperature for the next 3,000 seconds. So the surroundings is 20 degrees. So you would imagine that obviously this liquid can't get lower, can't go lower than 20 degrees. So I'm just going to mark that out there. I hope I'm going to be able to, my board is synchronized, so I'll be able to draw this. But it's obviously going to be a curve, and it's going to, as it gets closer to this 20 degree line, it's obviously going to get flatter and flatter. The rate of change, the rate of loss of temperature is going to get less and less because the temperature difference is getting less and less. So we're looking for the next 3,000 seconds. So we're basically going up to 6,000 here. So we need to extend the curve. So the curve needs to naturally extend, but start to get less and less. Maybe I'm going a little bit too sharp there. So we're going down. It's quite difficult for me to draw this, but so it's going to, in the end result, if you kept on drawing this, it would go like that, and it would be, you would have an asymptote relationship there. It would never actually reach that 20 degrees. So you would have something like that. It would be a curve that would become flatter and flatter as you go through. This needs to, over here, needs to not be disjointed, needs to just continue on with that curve. And you would have got 2 marks for that. I hope that's reasonably clear. If you need some help, I'll actually help you draw it on your graph or on a different one. So by reference to the graph, state and explain the rate of loss of thermal energy from 0 to 600. Now you've got 2 marks here, so make sure that you include enough for 2 marks. You can see here that the temperature is falling, so state and explain the rate of thermal energy from the substance between there. So there's obviously going to be a thermal energy transfer. So you're having thermal energy being transferred to the surroundings. As it's and it's, as you notice there, the curve is changing it's at a decreasing rate. I'll bring up the curve just now and just talk about it more. It's at its greatest at that time. It's at its greatest loss in this period. Basically because the temperature difference is at its greatest. Alright. Okay, so there we had something like you had the curve. It was going like this. You can see this is temperature and time. So it's actually getting flatter here. So the rate of change of temperature, so the actual heat loss, the energy loss, the thermal loss is decreasing, but still it's greatest at that time. And now from 600 to 800, it does something like that. So obviously at that time, there is a phase change. So you're getting again a loss of thermal energy. That is true, but it's not coming through a loss in temperature. The temperature is remaining the same. So where is this temperature coming? Where is it? What's happening there? Well, we are getting a change in the phase. So you're going to have a liquid changing into a solid in that. So you're having a phase change. There's a phase change taking place. There's 4 marks here, so you've really got to give quite a lot of detail. There's a phase change. The temperature is constant, therefore your kinetic energy is constant, but your energy outflow comes from that change. So is a potential energy outflow, a PE change, and you're actually lowering the potential energy. The potential energy is decreasing, so it's giving out energy to the surroundings. Alright, so we're getting energy being given out to the surroundings. So it's this loss of potential energy, and that is where the energy is coming from. Okay, that should probably get you your 4 marks. Good. Alright, then going on to this next one over here. I'm probably going to have to call up the graph again. So let's just have a look. Let's just go back to the graph, and I'll just read the question to you as it states here. It says the mass of the liquid is 0.11 kilograms, and the specific heat capacity of the liquid is 1300 joules per kilogram per Kelvin. Use the graph to deduce the rate of loss of energy at time is 600 seconds. So we're actually at this point over here. That is time 600 seconds is approximately 4 watts. Now you're going to use this formula over here, that your Q is equal to MC change in T, change in temperature. Obviously when we're talking about power, we can divide by time on both sides, and that becomes power is equal to MC change in T over T. Now this value over here we can actually get from the graph, because that here you've got your change in you've got your temperature, and here you've got your time. So the slope of this graph actually gives you this value at that point. Now it's quite difficult here, but you've actually got to get a ruler, and you've got to draw if you just imagine this line just continuing from this point as a straight line, so no longer, so you've got to draw a line down like that, and a line like that, and make it as big as you can, and then from that you actually work out this rate of change of temperature. Because the change of temperature here, this is going to be a little bit rough on my diagram, I'm not going to be getting it so well, but your change in temperature here, your change in T is say about 58 degrees, and your change in time is something like say 2,800 seconds. So your power is going to equal to the mass, which is 0.11, times the specific heat capacity. You're told your specific heat capacity for this is 1,300, so it's times 1,300 times this, so that's going to be 58 divided by 2,800, and when you find that all out, you should get to a value of somewhere around 4 watts. Your power should equal to 4 watts when you do that. Alright, so that was that question. Let me see if there's anything more that needs to be done here. Over the page, so there. And here calculate so that's the 4 watts there, calculate the specific latent heat of fusion of the liquid. Now we are obviously going to assume here that you've got 4 watts is the energy that's coming out. So if we can find the time, let's go back to my graph. Let's go back to the graph here, and sorry, let me get this out here. I'm having a problem with this. Just give me a moment here while this just goes. There it is. Now I can move it up. Alright, so we've got that the fusion took place over here, over there. Now this is probably, I'm not really seeing this actually. Let me just get a diagram here. I could be able to see it better on a paper diagram. This is going from about 600 to about 1,800. That's 1,800. So your time is that's actually involved during the phase change is 1,200 seconds, and it's at 4 watts. So if you get 4 watts, that's joules per second. If we multiply the two together, seconds are going to cancel. You're going to get your total joules. So that's going to be 4,800 joules. Now that 4,800 joules is all being lost to the surroundings, and that's equal to ml. So that's 0.1 times your specific latent heat. So it's 4,800. When you divide the two, you're going to get your answer for that. And it should be somewhere in the region that your L works out, somewhere in the region from 33 to 55 kilojoules per Kelvin. Per kilogram. Obviously this all depends on your value, because this over here required this value over there. Alright, so whatever value that you had for that, and you had to put it into that. Alright, hope that makes sense. Thank you very much.